This concept module will cover the concepts of coordinates and components. So to introduce the importance of this concept, I want to start with this example here. So we're on a basketball court, and let's say the circle is representing a player with the ball, wanting to get away from the two defending players who are represented by crosses. So they move from position A to position B like this. We may be interested in the distance, but it's unlikely to be the most important variable here, and it's also really hard to calculate, and we might be able to talk about that later in class. What might be more important though is calculating displacement, so that straight line between position A and position B, and in particular how far we've gone between those 2 points and the direction of that travel as well. So we can do that, we can calculate the direction from any line we draw in the basketball court, but in this example we might be most interested in the direction of travel from a line running horizontally across the court here. So how do we do that? How do we make those calculations? Well, we need a little help. We need something else. And so by introducing coordinates, which is essentially a grid system, over the top of this problem, we can suddenly find out a lot more information. And in particular, the great thing that those coordinates help us with is to create a right angle between the horizontal and vertical lines in that grid. And that happens inherently. And so if we count our horizontal lines across in this particular problem, or this vector that we've created, and the vertical lines up, then we've created ourselves a little right angled triangle, and we can now use information about the distance between those grids, which is 1 meter in this case, to calculate the angle or the direction as well as the magnitude of that displacement vector. So if we start with direction of that displacement vector, and we can count our grid lines horizontally, and they each represent a meter, so it's 6 meters across and 3 meters up in this grid system here, then we can just use a little bit of right angle trigonometry. And in particular, one equation within our right angle trigonometry set that we can use is tan of an angle within that triangle is equal to the magnitude of the opposite side divided by the magnitude of the adjacent side of that triangle. And in this case, if we're trying to solve for that particular angle you can see on the screen, the opposite side of that angle is 3 meters, and the adjacent side, the side next to that angle, is 6 meters. So if we input that in, tan of the angle equals 3 divided by 6, tan of the angle equals therefore 0.5. Now we need to get that angle by itself, so we have 0.5 divided by tan. Now to represent that on a calculator, you need to put in 0.5 tan inverse, or inverse tan. It's calculated differently in different calculators, so be aware of that. And the angle is therefore 26.57 degrees. If we're then interested in the magnitude of the displacement itself, which actually is the hypotenuse of this triangle, we can just use a bit of Pythagoras, another bit of right angle trigonometry calculation here. And we know that a squared and b squared, and there's the opposite and adjacent sides of the triangle, so the square of those added together equals the square of the hypotenuse side. So 6 squared add 3 squared equals our displacement in this case. So we just carry that calculation through to isolate the displacement. S is representing displacement, equals 6.7 meters. So in addition to calculating the displacement magnitude and direction, we might also be interested in the velocity of this play and the average acceleration during this particular play as well. Now, with respect to direction, the direction of the velocity and acceleration vector, as you can see here, is exactly the same. So it's exactly the same right angle trigonometry, exactly the same direction. However, the magnitude for velocity and the magnitude for acceleration will be different depending on time. And so if we already know our displacement, which is 6.7 meters, we've calculated here, and we've given time, so let's say that our coach has timed that particular play, or we can watch it back on the video and calculate that's 1.8 seconds, then we can simply put it into our equation of velocity equals change in displacement divided by change in time, 6.7 divided by 1.8, and our average velocity in this particular play was 3.72 meters per second. You could then go on and calculate acceleration as well, but hopefully it's clear now how the coordinates, or providing coordinates into an example and allowing us to break down a vector into its components allows a much easier calculation of these particular problems. As usual, it's really helpful to see these concepts explained in different ways, so please use these links here as well as searching some different resources online for yourself.